start in a few. I'll turn off the Santa behind me in a minute. But I'm just gonna go over some. I'm not gonna really go over the review packet. You have the key. I'll take questions, but you can check your answers. If you do have a question on the packet, let me know. I'm happy you like the music. Do you also see the Santa climbing behind me? He's putting up lights on the tree. It's awesome. So anyway, I'll turn down the music, but I'll keep the Santa going because he's Santa. All right, so like I said, if you have any questions in particular, feel free to text me on Remind throughout this. I'm going to focus on a few things, but if you have any particular questions, just let me know. So the first question, I'll settle this right now, was about drawing calcium fluoride in water. You know, how does it interact with the water molecules? So if you think of water on its own, the oxygen is always more electronegative than the hydrogen, and you can look that information up on Table S, or you can think about the trends. So that oxygen is always going to be partially, or kind of, and that's the symbol, negative. And hydrogen is going to be kind of positive, because the more electronegativity you have, the more likely you are to attract electrons. And electrons are negatively charged. So if you're attracting an electron closer to you, you're kind of negative. So whenever you dissolve any ionic compound in water, any metal or non-metal in water, the positively charged metal is going to be attracted to the kind of negative oxygen. And the charged non-metal, the negatively charged non-metal, is going to be attracted to the kind of positive hydrogen. So in any scenario, if you have a metal and a non-metal, the hydrogens of water will be attracted to the non-metal, and the oxygens of water will be attracted to the metal. And that's all I was really looking for there. That you have these ionic compounds that you know are positively and negatively charged, and you have this molecular compound that you know has these positive and negative areas, not charged, but they're like kind of negative over here, kind of positive over there. They will, through opposites attract. The positives and the negatives will hang out. The negatives and the positives will hang out. And that's that. Got a lot of questions on how to draw ionic compounds. So I'll do it the long way to just kind of show you the explanation, show you the chemistry behind it, and then kind of go over the short way. So let's say you were asked to draw CaF2 as a compound. How would you draw the Lewis structure? You cannot draw it like this. No. Because this is an ionic compound. In an ionic compound, you transfer electrons. Okay? You're transferring electrons here. So you can't draw a bond. This means you're sharing electrons. And that's just not happening. So, calcium has 2 valence electrons. Fluorine, both of them, have 7. Fluorine wants 8 to be happy. Calcium would prefer to lose those 2 to be happy. So it's going to take each of those and donate them to the fluorines so that the fluorine can have 8. And then the calcium loses those 2 so it can be happy. So your final answer is going to have your calcium with no electrons, because it got rid of them, with its charge. And then a fluorine with its 8 dots, with its charge. But since there are 2 fluorines, you're going to put a 2. So we know that there's 2 fluorines. So the general idea behind drawing any ionic compound, let's say you were doing NaCl. All right, if you're doing NaCl, take Na, put it in brackets with its charge. Always take the metal, put it in brackets with its positive charge, and draw no dots around it, because it's a metal. It's lost those electrons. It's given them to the nonmetal. Take the nonmetal, put it in brackets with its charge, and always show it with 8 electrons, because it got that 8th electron here, and I'll show it with an X, from the metal. And that's generally how you draw ionic compounds. You don't worry about shape names. You don't worry about polar and nonpolar. You don't worry about polar and nonpolar even with a bond. So this is no polar and nonpolar bonds. These have no polar or nonpolar molecules. These don't have shape names. These don't have lines. You just have a metal, positively charged, no electrons, and a nonmetal, negatively charged with 8. And that's it. That's how you draw ionic compounds. Another big question that comes up constantly in this unit is IMFs. What the heck is an IMF? I don't get what an IMF is. Ask Mr. G. We were a disaster this day. We weren't paying attention too well. What the heck were you talking about? What is an IMF? So, let's say you had, I'll go over each one individually. So there's 4 that you need to know. Let's say you had FF. Alright, so F2. This is a bond. How does F and F, how do they hang out? What are they doing? They form a bond. They form a covalent bond. They form a nonpolar covalent bond because they're the same atom. That's how this single molecule of F2 interact with each other. F line, F bond, boom. But how do these millions and millions and millions and millions of these F molecules interact with other F2 molecules? So how are all these FFs interacting with other FFs? What are they doing? So if you were to draw 2 FFs, how are they interacting in this space between the molecules? How are those, what is that attractive force there? Because they're not bonding there, because the bond is here. But like I said, there's an unimaginably large amount of these fluorine molecules in the atmosphere. How are they interacting with each other? This is the IMF. The intermolecular force of attraction that is taking separate molecules. I'll put that on, yeah. Thanks, Mrs. G. That takes these separate molecules and attracts them in some way. And the weaker that attraction, the lower the boiling point, the lower the melting point, the higher the vapor pressure. So, since fluorine, F2 is a gas at room temperature, we would say it has weak IMFs. Because it's really easy to turn into a vapor. And it's just floating around, going crazy. Because they're not attracting each other strongly. So, let's summarize that. A weak IMF equals a low boiling point and a high vapor pressure. Basically, all that's saying is this thing is really easy to turn into a gas. Like, really easy. Because their attraction for each other is so weak. Which means if you were to draw a particle diagram, they're all over the place. They don't want to hang out together. They're just everywhere. They have a very weak attraction for each other. versus another molecule, like let's say water, that IMF that exists between the different water molecules, like right here in this space and right here in this space, that's a stronger IMF because we know water is a liquid at room temperature. So if we imagine water as a particle diagram, they're not going to take up. They're going to be behaving more like a liquid. They're going to be more ordered, right? Less entropy, closer together. Trinity, I'll go over that in a minute. Closer together. Therefore, it's a stronger IMF. A stronger attraction means a stronger IMF, which means a higher boiling point. So if you have a high boiling point, which is the same as a low vapor pressure, because vapor pressure, what's that mean again, Mr. G? Vapor pressure is, what's the pressure of this gas pushing down on this liquid? So if you have a high boiling point, you're hard to turn into a gas. There's less vapor above the liquid. There's less vapor pressure. So this would mean you have a strong IMF. It's all about data. We can't say, oh, this IMF is strong. Hydrogen bonding is always strong. You can't say that. You have to use the data. Data determines the strength. But that being said, you do need to know the different types of IMFs that exist. So, the first one is called dispersion. And these exist in all molecules. So, if you're polar or nonpolar, and remember we're talking about covalent molecules here, nonmetals and nonmetals. So if you're polar or nonpolar, you have dispersion. But nonpolar only have this. Meaning of the four we're going to go over tonight, dispersion only, I said it the other way, nonpolar only have dispersion forces. That is the only IMF that exists between nonpolar molecules. So if you were to look at FF, and you want to identify what is this IMF exists between these fluorines, we would say dispersion, because fluorine is not polar. Therefore, the only attraction it has is dispersion. And we know for fluorine, this is a weak IMF. Because fluorine's a gas at STP. But the bigger you are, the bigger the molecule is, the stronger dispersion gets. So, for example, what I mean by bigger, I mean how big are you? How many electrons do you got? How big are you? So, iodine, I2, is in the same group as F2. They're in group 17. But F2 is an iodine is a solid. So even though they're both dispersion, these forces in I2 are strong. Because it's a solid, which means they're very, very attracted to each other. Because as we know, as a solid, it's ordered. They may or may not be closer together, but they're less chaotic, less entropy, more ordered. Versus fluorine, they must be pretty weak because it's a gas. So you got to look at the data, look at their boiling point, look at the phases they exist in. The phase and boiling points help determine the strength of your IMF, not the type of IMF. All right, the next IMF. Okay, a couple of questions we're getting. Let me pause for a minute. Let's look them over. Question. All right, what type of IMF is F2? Hit that. How do we know when something is a solid or liquid at STP? It either must tell you in the problem, maybe it'll say it in words, maybe it'll do like a little symbol, like I2, S. Maybe it doesn't tell you, and you can go to Table S. Because Table S has all that information on melting and boiling points. Maybe I just give you the melting and boiling point. You won't know. You won't just know. Other than water, which you can usually assume is a liquid at room temperature, I gotta tell you somehow, or there's gotta be something in the problem, or you gotta look it up on Table S, or something like that. Where do I buy that Santa that climbs up the tree? So I got this Santa at Target. He comes on this ladder. He pretends to put on lights. Mrs. G says he really puts on lights. And then it comes with this thing that just looks like his bag of toys. And it plays music. Okay. What's the other IMFs we need to know? IMF 2 is dipole. And dipole is the main IMF, because remember, dispersion is in all molecules, but the main IMF of polar molecules. So something like that's polar, like maybe HCl, for example, is going to have a dipole attraction. So the attraction between this H and this other HCl is a dipole attraction because it's a polar molecule. So the dispersion attraction still exists there, but the main attraction, the main IMF, is dipole. So that's IMF 2. IMF 3 is hydrogen bonding. So hydrogen bonding is a special type of dipole that only exists between an H and F, O, or N. So hydrogen bonding is fine. So in a molecule that has this IMF, like water, so the IMF is right here, that's the hydrogen bond. Not this. That's a real bond. That's a covalent bond. This hydrogen bond is, because an IMF is between molecules, not within. So no, not the hydrogen bond. Yes, that's the hydrogen bond. So it's exactly like dipole. It's just a special, unusually strong case of dipole where if all else is equal, meaning if H were bonded to any other elements in these groups, so 15, 16, or 17, you would notice that for whatever reason, meaning because of hydrogen bonding, an HN IMF will have a higher boiling point than an HP. An HO will have a higher boiling point than an HS. An HF will have a higher boiling point than an HCl because of this unusually strong attraction that we call a hydrogen bond. Okay, question. Haha, this hits a misconception. Are hydrogen bonds the strongest bonds? So, 1, the question should be, are hydrogen bonds the strongest IMF? And I'll say it like this. All else being equal, meaning they're similar, if hydrogen is bonded to an element that's chemically similar to the element it's bonded to in a hydrogen bond, so again, that would be like H2O versus H2S. H2O has a higher boiling point. So here we can say, because of hydrogen bonding, H2O has a higher boiling point. Because that's the only difference in IMFs between H2O and H2S. So H2O's main IMF is a hydrogen bond, versus H2S's main IMF is dipole. But we can't just say hydrogen bonding is the strongest IMF, because as we talked about earlier, I2, even though I2 is only dispersion, I2 is a solid. So, since it's a solid, that means that dispersion force in I2 is extremely strong, even stronger than the hydrogen bond in water, because at room temperature, water is a liquid. So we can't just say dipole is moderately strong and hydrogen bonding is the strongest, dispersion's the weakest. Doesn't work like that. Does not work like that. If hydrogen is bonded to something chemically similar to the group that N, O, and F are in, so 15, 16, and 17, because of that hydrogen bond, it will be a stronger IMF when you compare HO to something like HS, or HN to something like HP, or HF versus HCl. But you can't just say hydrogen bonds are stronger than all forces, because, again, dispersion force, I2 is a solid. Yet, NH3 has a hydrogen bond. NH3 is ammonia, and you know what ammonia is at room temperature? A gas. So you can't just say hydrogen bonding is the strongest. You have to compare it to other elements that are chemically similar to nitrogen, oxygen, and fluorine. And chemically similar means they're in the same group. Same group. Live stream, you're going through what you got for Christmas after Christmas. So, I'm an adult, which means Christmas is not as fun anymore. Mrs. G and I already exchanged gifts because Harper opened up Mrs. Geronda's gift for her to find on the floor, which was an Apple Watch that I got her. So, Mrs. G felt bad and gave to me what I got for Christmas from her, which was a Nintendo Switch. Other than that, my parents usually just give me money, so I'm probably not going to show off anything I got for Christmas. Alright, oh wait, hold on, a few more questions. Okay. Good question. When I'm talking about, especially in dipole here, when I say polar, I'm always going to be talking about the molecule. So that's a good question. Thank you. So I was talking about the molecule here. So dipole forces exist in polar molecules. So for example, carbon dioxide has polar bonds, non-polar molecule. This only has dispersion forces. This does not have dipole because it's a nonpolar molecule. Uh-oh. Who's here? Who's this? Who's this? Come here. Come say hi. Hi. Go get it. Thank you. Good question. Uh-oh. Oh, boy. I feel like she's going to annoy people now, Mrs. G.
Come on. You want to go out? Do you want to go outside?
Oh, yeah. See ya. I'll put her on camera when she comes back. She kind of got... She was like, hey, and then she went away. Okay. The last IMF is called ion dipole. And that's usually the simplest one. Because that's just when you take an ionic compound and you put it in something polar like water. And that, how are they interacting with each other? I drew that earlier. So this interaction, calcium fluoride and, where the heck is it? Calcium fluoride and water. This like, oh, the oxygens are hanging out with the calciums and the hydrogens are hanging out with the fluorines. That is the ion dipole IMF. So this right in here That's the IMF. So the other three IMFs only exist in covalent compounds or molecular compounds. If you take an ionic compound and you put it in water or anything else that's polar, you get ion dipole. That was really where I super wanted to focus, was IMFs, because I still felt like we were a little confused. Another question, hold on. Will ion dipole IMFs have a charge? So the ions do. So like the calcium does, and the fluorine does, but the water does not. So yes, no. Aside from that, you just got to use the data. Higher boiling point, stronger IMF. Tends to be a solid, stronger IMF. It's just all about how are these molecules attracting each other. Kind of like a magnet. So you have two magnets and they're really far apart. They have a weak attraction for each other. They're going to tend to stay far apart. Tend to stay like a gas. You get them closer together, if they have a strong attraction, boom, solid. Hard to break that attraction for them. They're not bonding, they're just attracted to each other. And that's an IMF. Anything else on the test is naming, which we've taken a few quizzes on. Bonding, which I just passed back, so that's like drawing the structures, naming the shapes. Is the molecule polar? Is the bond polar? Ionic versus covalent. The periodic trends and like electronegativity and ionization energy and atomic radius. Why do they increase going this way? Why do they decrease? Why do they decrease going that way? If you're removing electrons, what's happening? Okay. Polar versus nonpolar. Okay, bond. Polar when different. Look at electronegativity. So if you have two different atoms, it's usually polar. Very few exceptions. If you're not sure, look at their electronegativity. If their electronegativity is different, polar. The more different it is, the more polar it is. So oxygen and nitrogen, their electronegativities are pretty close. Not as polar as oxygen and hydrogen, whose electronegativities are further away. Polar molecule. Snap that bad boy. Look at the symmetry. Symmetry. Nonpolar. Asymmetry. Polar. Something like carbon tetrachloride. Look at that carbon. That's chlorine, that's chlorine, that's chlorine, that's chlorine, not polar. Because it's symmetrical. It's surrounded by chlorines. Each bond is the same type of bond, making it symmetrical, not polar. Look at something like ammonia. That's hydrogen. That's hydrogen. That's hydrogen. Polar. It's not surrounded by the same type of bond on each side because that lovely lone pair of electrons at the top, that's not hydrogen, throws off the symmetry. Polar. Favorite element is probably carbon because it's like super essential. Not the coolest element, but how can that not be your favorite? And I know you're going to be like, what about oxygen? It's needed to live. I feel that. I get it. But still, you can't survive without carbon either. DNA wouldn't exist. DNA is pretty cool. Gosh, shape names. How can I do this quickly? That's the thing. How can I do shape names quickly? I mean, we're going to do it, and it's going to be fast, so here we go. Element, element, linear. 3 elements, no lone pairs on the central atom. Linear. 3 bonds, and I'm putting carbon even though these molecules don't exist because it's easy to write C's. 3 bonds, 1 lone pair, trigonal pyramid. 2 bonds, 2 lone pairs, bent. 3 bonds, no lone pairs, trigonal planar. 4 bonds, tetrahedral. 5 bonds, trigonal bipyramid. 4 bonds, 1 lone pair, seesaw. 6 bonds, octahedral. No, don't have a trivia crack. I would destroy you. You would be embarrassed to play me in trivia crack. Alright. Those are the shapes. Trends. Going this way, we got radius, down, other 2. So electronegativity and ionization energy, up. Going this way, we got radius, up, other 2. Electronegativity, ionization energy, going down. Going back that way, we got radius, up, electronegativity and energy going down. And then completing the square or rectangle, we got radius, down, electronegativity and ionization energy going up. Those are the trends. Let's see. Isn't asymmetrical nonpolar? No. Symmetry, nonpolar, asymmetry, polar. Snap it up. Alright, what explains these trends? Going this way, more protons. Electrons are staying in the same shell. You have a higher nuclear charge. The more protons you have, the closer you're attracting the electrons. That makes the radius smaller. That makes the other 2 go up. Going down, electrons in shells. I have a request that Harper needs to make an appearance, so she needs to come down here.
Really busy eating bunny food right now.
That's nice. So, going that way, more protons, higher nuclear charge, makes the radius small, makes the other 2 big. Going that way, the electrons are getting further and further and further and further and further away, making the radius bigger and bigger and bigger and bigger and bigger. Makes the other 2 go down, doobie-doo, down, down. Test is like 30-something questions.
Oh, that's too close.
Box Mommy is a gift from my aunt. It's just like a slightly bigger television that she's used to having, and I think she'll appreciate that. Come here, girl. Come say hi. Come say hi. Harper, come here. Come here. Hi. Oh, yeah, thank you. Hello. Hello. Yes. Who's that? You can't see anybody, but they can see you. See ya. What else? Because I'm feeling wrapping this up because I'm not feeling like going any further. So naming, bonding, drawing, polar, not polar, trends, IMFs. You got a study guide with a key. What else? I'll take a few more questions. Coolest element? What's the coolest element? That's a tough question. Define cool. A lot of the transition metals are pretty cool because they have a lot of different colors. So, like, some of them are like blue and purple. And I'm not just talking about like when you burn them, like when we did that lab, because those were salts. I mean, they just like form cool colors. Fluorine's pretty cool just because it's so darn reactive. So it's like kind of cool, kind of dangerous at the same time. Cool, like does cool stuff or looks cool. Curium, pretty cool element. It's a metal. It's discovered by Marie Curie. It can like glow in the dark. It's radioactive. That's pretty neat. What was the thing you told us to remember about FR? So francium, fatty Frankie. It's the fattest element on the periodic table, meaning it has the biggest radius. So it's like your benchmark for radius. Start here. Nothing can get bigger than francium. And then fluorine is your benchmark for the other two. Well, let me say this. Fluorine is your benchmark for electronegativity, because fluorine has the highest electronegativity. Speaking of francium, like, francium's also kind of cool. I don't know if it does cool things, but as soon as you discover it, about 10 minutes later, it's, like, gone. It only exists as, like, a single atom. So, it's pretty neat. Again, I do love carbon, because, like, as boring as you might think it is, carbon is the only thing in diamonds, and, like, graphite, and all this other stuff. Like, carbon's everywhere. I think diamonds are pretty cool, even though they're not rare. That's a lie. Aside from that, I mean, I don't know. Gold, neat, but all the elements are like, they're fine. It's compounds is where it gets cool. Compounds is where it's at. Alright. Santa's getting turned off, which means the live stream is stopping. Someone wanted to see like the ornaments on my tree. So my tree this year is kind of boring because we're traveling. So we just kind of panic purchased a like a 6-foot, $30 tree from Target. But a lot of ornaments are like my grandma made. So she would like hand sew Snow White and the Seven Dwarfs here. So like she made this. So that's Snow White and like all the dwarves. I got Doc over here. Sorry, I'm on my computer, so I'm like trying my best to show these pictures. It's like a picture of our wedding day. You know, our first home. It's cute. This is our first house. You know, other things my grandma sewed. Mrs. G's a Giants fan. So we gotta have a little giant represent on the tree. Harper. She's pretty neat. We love her. But yeah, I mean, it's nothing to really like brag about, but it's our tree. It's, like I said, it's small. It's not like a big tree. It doesn't like span the room. But we are a real tree family. We just didn't get one this year because we were traveling. So we didn't want it to die or catch on fire or anything like that. But most of the ornaments on here are just like they were made by my grandma. She was like a pretty talented lady. So, let's see. Any other questions? Heck yeah, there's a Jets ornament. Don't you worry about that. Don't worry about that. I must get a Jets ornament every year. Mrs. G probably just hid it somewhere out of sight. She sure did. She sure did. Mrs. G. I see you hiding that Jets ornament. Huh? She's ignoring me because she knows. Because she hid it. It's back here, out of sight, probably where it belongs. She's not lying. But there's Jets. Come on, Mrs. G. See? Family. Oh, did we get him a Jets ornament? We don't remember. Better get him a sled again. Go Tar Heels. Come on, Mrs. G. I can't believe that. Hiding my Jets ornament. Both of them. Boo Jets and Giants. Are you a Bills fan? Terrible. All right. That about wraps things up. Ladies and gentlemen, mainly the three people that have been texting me this whole time. Thanks for watching.